We are now looking into Hawthorn effects. These are effects which come about because the participants in a study know that they are in a study, and they also know that they are observed in this study. So for example, here we have an example that when clinicians know they're being watched, patients fare better. Okay, so if the doctor knows that someone is observing him or her, then the patient gets better treatment. Okay, and likewise, for example, if you're observing a customer, then that customer may change his or her behavior based on the fact that the customer is being watched and knows that he or she is in a study. Okay, so it's really important to have a randomized trial with which the object in question does not know he or she is being observed. Okay, so we have a last example here for lecture 4, and that's Colgate versus Solidux. Okay, and for example, Colgate and Solidux are two brands of toothpaste. Okay, and they have each a whitening toothpaste. So Colgate has developed a new formula, and they would like to know whether or not it is more effective than the competition, Solidux. So they have 150 people in the treatment group, and they use Colgate for 3 days, and 220 people in the control group used Solidux. And we just assume that these people are picked at random, okay? Otherwise, we are in trouble. After 3 days, 72% of the treatment group had whiter teeth in comparison with 60% in the control group, which is Solidux. Okay, as a data scientist at the company, you have been tasked with analyzing the data from the experiment. So, the question is, do the results of experiment show that Colgate is better at teeth whitening than Solidux? Use the 5% confidence interval. Okay, so what we know is the Colgate sample contains 150 people, and the Solidux sample contains 220 people, and the Colgate, so it's like Colgate and Solidux, and the Colgate treatment group had 72% which got whiter teeth. Okay, and 60% in the Solidux group got whiter teeth. So now we know the proportions and we know the sample sizes, so we can actually compare. Okay, so and we use the 5% significance level. Okay, so what we do is we first check if we have enough sample. Okay, and remember that we need there to be 10 people. Let's see, sample size condition. Okay, so we need there to be 10 people in each group that were a hit and a miss. Okay, and from the top of our heads, we see that 72% got whiter teeth. That's 72% of 150 people. That's more than 10, and 28% did not get whiter teeth from the Colgate group. So that's 28% of 150, So that's also more than 10. And doing the same exercise with the Solidux sample, we see that there are more than 10 hits and misses. Okay, so needs to be more than 10, and it's okay. So the second point is what will cause you to change. Okay, what will cause you to change, for example, from Solidux to Colgate? Well, then you have an hypothesis, and the hypothesis is the proportion of Colgate is larger than the proportion of Solidux. Okay, which means the proportion of Colgate minus the proportion of Solidux is greater than 0. Okay, and the null hypothesis is the rest of the incidents. So that would be this difference in proportions would be less than or equal to 0. Okay, and the third point is to create the test statistic. So z-stat. Okay, and we know that the z-stat, it's the sample proportion difference. That is the sample proportion of Colgate minus sample proportion of Solidux divided by the standard error of this difference, P Colgate hat minus P Solidux hat. Okay, and we know the proportions because the P Colgate hat is 0.72 and P Solidux hat is 0.60. Okay, so what we do is that we just take 0.72 minus 0.6 divided by the square root of 0.72 times 0.28. That's 0.28 is 1 minus 0.72 divided by the sample size for Colgate plus 0.6 times 0.4 divided by the sample size of Solidux. Okay, and if we calculate this, then we get an answer of 2.43, and that's our z-stat. Okay, so these are our hypotheses, and now you need to know the critical value. And what you do is that you look up in the Z table and get the for example, one-sided, and here is the one-sided test. It's 1.44, and the critical value is 1.464, I mean. And then you test, is the z-stat greater than critical value, and 2.43 is greater than 1.64, so we reject H0. Okay, So what we find is that the results of the experiment show that Colgate is better at teeth whitening than Solidux at the 5% level. Okay. And question B, the marketing head at Colgate wants to change the packaging to say you're 30% percentage points more likely to get whiter teeth with Colgate than Solidux. Okay, how would you respond? Okay, take 5 seconds to just think about it. Okay, so what we have is that we know the difference of success. The success rate is different in these two in these two samples. Okay, and it's statistically significant at the 5% level. Okay, but to say that you're 30 percentage points more likely to get whiter teeth with Colgate than Solidux is quite a strong statement, okay? Because then you treat this as the truth, but it's not, okay? It's just one out of an infinite possibility of samples, right? So you can say that you're over 95% confident that the difference is greater than 0, but you can't specify it exactly, okay? So basically, what you should know after this lecture is that observational studies may suffer from confounding variables, okay? Those variables you can't really see. And even if you observe a pattern in your data, you have to check or think what kind of causal effect might be the cause of this, okay? And what kind of alternative stories are there for the observed patterns, okay? Because often you would kind of fall in love with one possible explanation and downplay the importance of other explanations, which is quite dangerous. So if you use experiments or A/B tests, then you can isolate the cause or the factor that you think is the cause of a difference between two populations, okay? And you then use 2 sample t-tests or c-tests, t-tests for mean and c-tests for proportions, and you test whether or not they are different from 0 or another value, okay? And you can use a two sample confidence interval for the difference in means or proportions to get a range of values, okay? Because then you can say something about the probability that the true difference is within a certain confidence interval. Okay? See you next time.